A sidewalk can hold up a truck, yet it starts as loose gray powder. A skyscraper can stand for 100 years, yet its foundation begins as crushed rock and ash. Cement is one of the most used materials on Earth, but almost nobody knows it isn't the same thing as concrete. That shouldn't be possible from something this ordinary. So how do factories turn limestone, clay, and fire into a powder that holds up entire cities every single day, all over the world? Let's step inside and find out. Most people think cement and concrete are the same material. They're not. Concrete is the sidewalk, the wall, the bridge, the finished product. Cement is just one ingredient in it, the part that acts like glue. Mix cement with water, sand, and gravel, and you get concrete. Without cement, none of it holds together. And here's the part that sounds impossible. This glue starts its life as ordinary rock, and it's turned into powder using heat almost as hot as the surface of Venus. It begins in a quarry where massive excavators tear into a hillside of limestone. Limestone makes up about 80% of what goes into cement, and it's mixed with smaller amounts of clay, sand, and iron ore. Materials chosen because together they contain almost exactly the calcium, silicon, aluminum, and iron the final product needs. Geologists actually study a quarry for years before a plant is ever built there, because the exact chemical makeup of the rock changes from one hillside to the next. And a plant needs a supply that will stay consistent for decades. Trucks the size of houses haul the raw rock to a crusher, which smashes boulders down to fist-sized chunks in seconds. From there, the crushed rock rides a conveyor belt toward the heart of the operation, a plant that never stops running 24 hours a day, because shutting it down and restarting costs more than keeping the fire burning. Some of these conveyor systems stretch for miles, snaking from the quarry straight into the plant, so trucks barely have to move the material at all. The crushed limestone and clay are ground into a fine powder, smaller than table salt, inside massive rotating mills packed with steel balls that crush the rock as the mill spins. This mixture is called raw meal, and it needs to be almost perfectly uniform, because even a small imbalance in the mix will weaken every bag of cement it eventually becomes. Sensors constantly analyze the powder as it moves through the plant, adjusting the blend in real time the way a chef might taste and adjust a recipe mid-cook. Except here the recipe is being corrected by computer thousands of times a day. The raw meal doesn't go straight into the fire. First, it climbs through a preheater tower, a stack of cyclone chambers 5 or 6 stories tall. As the powder falls through, it meets rising hot gases traveling the opposite direction, heating the material to over 800 degrees Celsius before it even reaches the flame. This step alone saves enormous amounts of fuel, because the plant is essentially recycling its own heat instead of generating all of it from scratch inside the kiln. This is where the transformation happens. The preheated powder enters a rotary kiln, a massive steel cylinder, sometimes longer than a football field, lined with heat-resistant brick and tilted slightly so gravity slowly pulls material through as it spins. At the far end, a flame burns at nearly 1,450 degrees Celsius, hot enough to partially melt the rock. As the material tumbles through that heat, it undergoes a chemical transformation called calcination. Carbon dioxide is driven out of the limestone, and the remaining material fuses into small gray pellets called clinker. This single kiln is, in a very real sense, the most important few hundred feet of the entire operation. Everything before it is preparation, and everything after it is refinement. The glowing clinker drops out of the kiln at over 1,000 degrees and hits a cooler, where blasts of air rapidly bring the temperature down. This isn't just for safety. Cooling the clinker quickly locks in the specific mineral structure that gives cement its strength. Cool it too slowly, and the crystals inside the clinker would form differently, producing a weaker final product. Some of that hot air captured during cooling gets piped right back toward the kiln or the preheater tower, squeezing even more efficiency out of heat that would otherwise be wasted. The cooled clinker looks like dark, rocky marbles at this point, not powder at all. It's fed into another mill along with a small amount of gypsum and ground down one final time into the fine gray powder that gets loaded into bags and silos. That tiny addition of gypsum is what controls how fast the cement will set once water is added later at a construction site. Without it, cement would harden almost instantly after mixing, long before workers could ever pour it into a foundation or mold. Cement itself isn't new. The Romans were mixing volcanic ash with lime nearly 2,000 years ago to build structures like the Pantheon, whose concrete dome is still standing without a single reinforcing steel bar inside it. That recipe was lost for over 1,000 years after the fall of the Roman Empire, and it wasn't until the early 1800s that a British bricklayer patented what we now call Portland cement, named after a type of stone it resembled. Using essentially the same limestone and clay process modern plants still rely on today. What's changed since then isn't the basic chemistry. It's the scale, the precision, and the speed at which a single plant can now turn out that same ancient recipe. Not all cement is the same either. Depending on the ratio of ingredients and how finely it's ground, plants produce different types built for different jobs. One type designed to resist salt water for coastal construction, another built to set faster for repair work, another engineered to release less heat as it cures so it doesn't crack in massive structures like dams. A single plant might run several of these formulas in rotation, switching recipes the way a bakery might switch between different kinds of bread using the same basic oven. Here's the detail that surprises almost everyone. Cement doesn't actually dry when it hardens. It cures through a chemical reaction with water called hydration that can continue for years. That's why a concrete structure isn't at its full strength the day it's poured. It keeps getting stronger for decades. Some ancient Roman concrete mixed with volcanic ash has been curing and strengthening for nearly 2,000 years, and modern engineers are still studying why it's outlasting some concrete poured last century. From a hillside of gray rock to a fine powder sealed in paper bags or pumped into rail cars, the journey takes raw material through crushing, grinding, a tower of rising heat, a kiln hot enough to reshape stone, and a final grind that turns rock into dust. What started as limestone and clay is now the single most produced material on the planet by weight, quietly waiting in a bag until someone adds water and turns it into a sidewalk, a bridge, or the foundation of a 100-story tower. Scale is where cement becomes almost hard to picture. A single large plant can produce over 1 million tons of cement in a year, enough to pour thousands of miles of sidewalk. Globally, cement production is measured in the billions of tons annually, more than almost any other manufactured material on Earth. Put another way, humans now produce more cement by weight each year than almost anything else we make combined. Laid end to end, the concrete poured worldwide in a single year could pave a road looping around the planet many times over. And every mile of it traces back to the same handful of steps happening inside plants like this one. That scale comes with a trade-off worth knowing about. The kiln's extreme heat isn't just energy intensive. The chemical process of turning limestone into clinker releases carbon dioxide as a direct byproduct of the reaction itself, not just from burning fuel. It's one of the reasons cement manufacturing is one of the industries most closely watched for emissions, and why some plants are experimenting with alternative fuels like shredded tires and agricultural waste, captured carbon systems, and modified recipes that need less limestone to begin with. A few newer plants are even testing ways to inject captured carbon dioxide directly back into curing concrete, locking the gas permanently into the material instead of releasing it into the atmosphere. Quality control never stops during any of this. Samples are pulled constantly, from the raw meal to the finished powder, and tested in on-site labs, sometimes crushed under hydraulic presses, just to measure exactly how much force it takes to break them. A shift of even 1% or 2% in the chemical ratio can change how fast the cement sets or how strong it becomes weeks later. Which is why, despite operating at an almost industrial plant scale, the entire process is monitored down to fractions of 1%, every single hour, every single day. Even the packaging is engineered. Cement absorbs moisture from the air the moment it's exposed, which is why bags are lined to keep them airtight and why silos storing bulk cement are sealed and pressurized. A bag of cement left open in a humid garage can start hardening on its own within days, which is a small reminder that the chemical reaction inside this material never really stops. It's simply waiting for water. That's how a hillside of ordinary gray rock becomes the powder holding up sidewalks, bridges, and skyscrapers around the world. Heat, precision, and chemistry most of us never think about. Until now.